Hi, welcome back. Today we're going to take a look at comparing derivatives. You're going to see a lot of old friends here. Everything should almost look the same as what we've been working on. So if we take a look here, we're given a graph of a derivative. Now we've seen this quite a bit. Now that's an ugly looking derivative. That's what happens when the teacher draws them. And this is the graph of the derivative. So let's write out what we already know. If we're above the x-axis, we know that the slope is positive. Below, the slope is negative, and our critical numbers are going to be on the x-axis themselves. But let's talk about some other things we need to also know. If we look down here, right here where the slope is 0, this is a minimum on the derivative. We know that this is where the concavity is going to change. So our second derivative is 0, and that occurs up here as well. I'm just starting to label all of my parts. Now, it kind of looks like I have a horizontal tangent here as well, but maybe not. I'm not quite sure, so no ambiguity here, so we're not going to worry about that. Now, the first question says, where is the graph of f increasing? Well, this is my derivative graph, so of course we are going to need our critical numbers, and this is where the derivative is 0, or d and e. And we already have them. Where is it 0? It's going to be at negative 2 and 4. So I'm going to write those down, negative 2 and 4. Doing our sign chart, it kind of looks like it goes on forever. So we're looking at negative 2 and 4. And let's see here, we're looking at the sign, so are we above the x-axis or below? Before negative 2, we're below, so we know it's decreasing. Between negative and 4, we're above. So that means that the slope is positive, which means that the function is increasing in value there. And after 4, it's also above the x-axis, so it's again increasing as well. So we want to know where is f increasing. We can say f is increasing on where the slope is positive, negative 2 to 4, or 4 to infinity, and that is because the derivative is positive. We've done this a million times now. Where is f decreasing? Well, that's where the slope is negative. So we can say f is decreasing on the domain negative infinity to negative 2, where the slope is negative, therefore, because the derivative is negative. Very easy to do. Next, it asks, for which values do we have a local max or min? Of course, in values. Just there we go. Typo there. Sorry about it. So we're looking for local max. These are another word for our relatives. So I know I have a relative minimum at negative 2, because remember, for a minimum we go down and then up. So we can say f has a relative minimum at x equals negative 2, and that is because the derivative goes from negative to positive. Do we have a local max? Well, if you remember, for a local max we have to go up and down. This goes up and up, but it never goes back down. Remember, because my derivative says we're decreasing here, and then any other time we're increasing forever. So this does not have a local minimum. A local maximum. So we can say f has no relative, and if you want to say local, that's fine too. I'm used to saying relative. Relative maximum. There's our answer. Piece of cake. All right, here we go. Here we're given again the first derivative again, and we want to answer the following questions. Now, if you notice the questions here, now they're talking concavity. So anytime we deal with concavity, that's our second derivative. So we're looking for the slope of the derivative graph here. And this is my derivative graph, so we're looking for the slope of the derivative equal to 0 or d and e. So we're going to go ahead and start by talking about our possible points of inflection. This is where the second derivative is 0 or d and e. And again, because this is the graph of our derivative, we are looking at their slopes. And of course, where is the slope 0? It looks to be here at negative 1. So there's my slope is 0, so that's where POI is, at 1. This is where the second derivative is 0. And it looks to be at positive 3. So my possible points of inflection are going to be negative 1, 1, and 3. And I'm going to do my sign chart. I'll do it down here. So I'll do my sign chart. Again, it kind of looks like, this one kind of looks like it stops at negative 3 and ends at 5. So we have a domain restriction here. Negative 1, and 1, and 3. And again, we're looking at the slopes, not the signs. So between -3 and -1, notice my slope is 0. Well, that's telling me that my derivative is decreasing. And let's go and write this out. The derivative is decreasing. Therefore, we say that's concave down. So between -3 and -1, it's negative, so it's concave down. Positive slope here, that's going to be increasing, so the derivative is increasing, that's concave up. The slope is negative here, that's our concave down. And positive here, that's going to be concave up. So we can say f is concave up on the following domains, -1 to 1, or 3 to 5, and that is because the derivative is positive. We can say f is concave down on the domain -3 to -1, or looks like 1 to 3, and that is because the derivative is less than 0. And next it says, do we have any points of inflection? Well, that's where our concavity changes. At -1, we go from negative to positive, 1 and 3. So we can say we have POIs at x equals -1, 1, and 3, and that is because two reasons. One, the second derivative is 0 or d and e, and 2, the second derivative changes signs. And there we go. All that. We've been doing this like for about 2 weeks now, so we should be good at these almost. All right. So let me go ahead and stop the video here, and then I'll let you guys go into video 2, where we'll continue on with today's lesson. I'll see you then.